Okay, so let's go ahead and start. So first of all, hello everyone. It's a pleasure being here, and it's a pleasure meeting everyone. And welcome to today's session on YOLO object detection. Now, YOLO, guys, basically it stands for you only look once. It's a very powerful and efficient algorithm in the field of computer vision. Today, we'll be delving into what YOLO is, how it works, and why it's become a significant breakthrough in object detection. Now, in the next few slides, guys, we'll be embarking on a journey into the fascinating realm of YOLO object detection, as we mentioned. So we'll start off by just understanding the fundamentals of object detection, exploring why YOLO specifically stands out in this field, and then we'll focus on the evolutionary path of the YOLO models from basically their inception to the latest version, which is YOLO v9. We'll also be diving deep into the architecture of the YOLO models and uncover the mechanics behind this efficient object detection. We'll also be discovering the specific reasons behind the adoption of the YOLO v8 model and its advancement. Now, finally, guys, gear up for an exciting hands-on training session where you'll get the opportunity to implement YOLO for object detection. So let's go on and start a bit. Now, before we do that, I'd like to just introduce myself a bit. I'm Jean-Pierre Fakhry, and I'll be your instructor in today's exploration of the YOLO object detection. So I have a background as a machine learning engineer, as mentioned at Orion, and I also hold 3 AWS certifications. Now, also, guys, as a technical instructor and mentor at Beirut AI, my passion lies in sharing knowledge and fostering a collaborative learning environment. So feel free to connect with me on LinkedIn, on LinkedIn, guys, sorry, for any ongoing discussions, questions, or even to explore more about the exciting world of machine learning and AI. So now let's go on and dive into the world of YOLO together. Now, before we do that, guys, we're gonna start off by explaining what is object detection. So object detection, guys, has a few fundamentals. So basically, it is a crucial task in computer vision that basically involves three main components. So first of all, we have detection, and this is the process of determining whether an object is present in the image. So basically, it answers the question, is there an object here? Now, after doing the detection, we have the localization. Now, for the localization, basically, once an object is detected, localization basically involves drawing a bounding box around the object, basically. Now, this, what we call bounding box, basically defines the spatial extent of the detected object in the image that we have. Now, after doing the localization, we have the last step, which is classification. So basically, guys, after the detection and the localization, basically the system will aim to recognize or classify the object. Now, this step focuses on assigning a label or a category to the detected object. Basically, we would be focusing on answering the question, what type of object is it, basically? Now, understanding these components is fundamental for us to grasp the details, if you want, of object detection. It's this combination of detection, localization, and recognition that forms basically the basis for advanced techniques like YOLO object detection. So now we're gonna go over a small example of how it works. So as we mentioned, guys, object detection at its core is the seamless integration of detection, localization, and recognition for multiple objects within a single frame or a single image. Now, in real-world scenarios, images often contain a multitude of objects, and each requiring basically identification and classification. Now, this holistic approach enables object detection systems to basically analyze and understand complex scenes, which makes it a key component in various applications, from basically surveillance cameras to even autonomous vehicles, for example, like what Tesla are doing. Now here, We have in this example that we have here, guys, we have an image that contains a scene with two cats and a ball that are placed on a table. Let's go on and just explore how would we tackle this as an object detection model. So first of all, as we mentioned, we have three steps. We're going to start off with the first one, which is detection. Here, basically, the object detection system will first scan the entire image, and it will identify areas where objects are present. Basically, here in this example, it will detect the presence of two cats, okay, and also a ball in distinct regions of the image. Now, after going through detection, we're going to start off with the second step, which is the localization. So, for example, for the detected cat, the system will draw a bounding box that we can see here, basically around the cat's positions, precisely outlining its spatial extent. Now, similarly, a bounding box will be drawn around the ball as well, and as we can see in red, indicating its location on the actual table. Now, for the last part, we have the recognition or classification. And here, after the actual localization, the system here will basically recognize and classify each object within its respective bounding box. So here, the cat is classified as a cat, as we can see, and the ball is recognized as a ball. Now, by combining these steps, guys, for both the cat and the ball, the object detection system here will provide a comprehensive understanding of the image, indicating the presence, the location, and even the category of each object that we have. Now, we do have a lot of challenges, guys, in object detection. As you can see, it can be quite challenging. So here, as we said, it can present several challenges due to the diverse nature of real-world AI images. And also, guys, one thing to mention is that a single image can introduce a lot of complexities, such as, so first of all, we have, for example, variability, lighting, orientation, even size. So here, for example, objects may have different lighting conditions, orientations, and sizes within the same image, which will make the detection very challenging. Now, another thing that we might stumble upon is, for example, random spatial distribution. So, for example, guys, objects can appear anywhere within the image, requiring the detection system to be robust and capable of identifying objects in various spatial locations. We also have, for example, overlap and occlusion. Here, in this example, basically, objects might overlap or be partially occluded by other elements in the image. And here, basically, this will demand a sophisticated technique to handle these specific scenarios. And at last, we have some challenges which are related to intra-class variations. Here, for example, even within the same category, objects may exhibit some variations, such as, for example, different breeds of dogs, different breeds of cats, or even, as we can see in this image, multiple types of vehicles. And addressing these challenges that we just spoke about is very crucial for the effectiveness of the object detection algorithm. So now, why are we deciding to use the YOLO model? Now, YOLO is very known to its accuracy to efficiency ratio. One of the key reasons why YOLO has gained immense popularity in the computer vision field is its exceptional accuracy to efficiency ratio. And YOLO, guys, YOLO models strike a unique balance. Okay, so what they can do is that they can offer high accuracy. So YOLO constantly basically delivers high accuracy in object detection tasks by basically considering the entire image in a single pass. It will be able to capture contextual information and effectively leading to precise detection. So apart from the high accuracy, it can also deliver efficiency. So YOLO's efficiency is unparalleled, guys. And this is very important to keep in mind because its ability to process images rapidly makes it very well suited for real-time applications. And here, guys, the single pass approach that YOLO has significantly reduces computational overhead compared to multi-stage detection models. So, as we mentioned, This winning combination of accuracy and efficiency makes YOLO a preferred choice for a wide range of applications, from real-time video analysis, for example, where you need to deploy the model and have real-time analysis. So YOLO is very good in that. Basically, also resource constrained environments as well, where YOLO can definitely stand out. So now we're going to be talking a bit about the history of the YOLO models and just explore them one by one. So we're going to, as we mentioned, talk about the evolution of the YOLO model. So we start off with the YOLO V1. And this was released, guys, back in June 8th, 2015. So it's a very old model. It's almost 9 years old. And the inaugural, basically, YOLO model was introduced by Joseph Redman. Okay, and this marked a significant breakthrough in object action. And what YOLO V1 guys did is that it basically pioneered the concept of processing the entire image in a single pass, which basically helped set the stage for subsequent advancement in efficiency and accuracy. Now, after YOLO V1, YOLO V2 came, and here what basically was added is some improvements and enhancements. So, building upon the success of YOLO V1, YOLO V2 introduced some key enhancements, and these included the incorporation of batch normalization, for example, basically improve training stability. Also, basically higher input resolution was introduced, as well as the introduction of anchor boxes for more accurate bounding box prediction. And these, we will be discussing them later on. Now, after YOLO V2 came along, we got YOLO V3, and this model was released in June 2018. And basically, guys, YOLO V3 took a giant leap forward by basically adding connections to the backbone network layers. And this allowed the model to make predictions three separate levels of granularity, significantly basically improving performance on smaller objects. So YOLO V3, guys, further solidified YOLO's position as a very robust and versatile object detection solution. Now, after YOLO V3, YOLO V4 came along, and basically YOLO V4, guys, represents a notable advancement over YOLO V3 as well, introducing some improvements to the model architecture that resulted also in a substantial boost in both the accuracy and the frames per second, or FPS. Now, this version also further solidified YOLO's standing as a state-of-the-art object detection solution. Now, after YOLO V4, YOLO V5 came along, and it directly succeeded YOLO V4, and it is an improvement over YOLO V3. Now, YOLO, notably, guys, this is very important to know. YOLO V5 doesn't have a traditional research paper that is associated with it. So this is very important to keep in mind. But nevertheless, it has gained attention for its performance improvement and also its ease of use, which makes it also a very notable choice for practical applications. Now, after YOLO V5, we have YOLO V6, which is a specialized object detection framework, and it's basically designed for industrial applications because it features hardware friendly and efficient design. And basically, guys, it is tailored to meet the specific requirement of industrial use cases, where basically the resource efficiency and real-time performance are paramount. Now, these recent iterations, guys, showcase the continuous evolution and adaptability of YOLO models, address the specific challenges, and cater to some diverse application domains. Now, after YOLO V6, we have the last three models, which are V7, V8, V9. Let's discuss them. So for YOLO V7, guys, it has set a remarkable benchmark by surpassing all the known object detectors in the speed accuracy trade-off. So basically, this means that it achieves exceptional accuracy without compromising on processing speed. And it's a testament to the ongoing efforts to find the right balance in real-time object detection. Now, after YOLO V7, we got V8, which is a state-of-the-art model. And here, guys, we encounter a state-of-the-art model, and it's one of the latest and most advanced versions in the YOLO series. and it boasts some enhanced features which YOLO V9 doesn't have. So it has not only detection, but it only has image segmentation, pose estimation, tracking, and even classification. It also has some increased flexibility and improved efficiency. So YOLO V8, what it does is that it builds on the success of its predecessors, incorporating cutting-edge technologies to be able to push, if you want, the boundaries of what's possible in object detection. And now we have the last or the latest model, which is YOLO V9. And as we mentioned, YOLO V9 is the latest YOLO model, and it was released very, very recently. And this model, guys, basically marks a significant leap forward because it introduced groundbreaking techniques like the programmable gradient information, which is also called PGI, and the generalized efficient layer aggregation networks, or GLAN. Now, YOLO V9, something that's very important to know about it is that it achieved exceptional accuracy and efficiency, and it set new benchmarks on data sets like, for example, the COCO dataset. Now, the YOLO series, guys, has constantly pushed the boundaries, as you can see, object detection, and each iteration is bringing us closer to achieving optimal performance in various applications. So here, guys, we can see the YOLO V8 architecture in this image that we have here, and we won't be delving too deeply into the specifics of it, but let's highlight some key differences from its predecessors. So for the visual representations, guys, we'll refer to a layout that you can see here that is created by Range King on GitHub, which provides us with a great visualization of the architecture itself. Now, the YOLO V8 architecture, guys, employs basically essential components for efficient object detection. So we have the backbone that you can see here, and it consists of convolution layers extracting relevant features from the input image. We also have the SPPF layer, or the spatial pyramid pooling fast layer, which is a technique that is used in some object detection architectures, and it involves a lot of pooling features at multiple scales to basically capture the context effectively. And also it has subsequent convolution layers, basically process features at various scales, while also it has some upsample layers, which can increase the resolution of the feature maps. Now, the C2F module that we have here also enhances the detection accuracy by combining the high-level features with contextual information as well. Now also, guys, finally, the detection module uses convolution and linear layers to map high-dimensional features, output bounding boxes, and object classes. Now, as you guys can see, designed for speed and efficiency, YOLO V8 maintains high detection accuracy, as you guys can see. And in our visual representation, one thing to mention that basically rectangles represent layers that are labeled basically with the layer type. So we have either convolution, for example, we have upsample, and so on. And we have also the relevant parameters. While the arrows that we can see also, they illustrate basically the data flow between the layers, with the arrow direction indicating the flow of the data from one layer to the next, basically. So now we're going to be discussing a bit of basically how YOLO detects the object. So basically, how does it work? So now basically, guys, YOLO operates on the principle of basically dividing the input image into a grid and basically focusing on predicting the bounding boxes and class probabilities. And here's an overview of that. First of all, we're going to start off by the input. First of all, what it does is that it takes an input image. As you can see here, we're giving it this image of a truck, and it divides it into a fixed grid size. Here, for example, 19 by 19. Now, the image, guys, as we mentioned, it will be divided into a grid. Please say, for example, 19 by 19, as you can see here, or it can be even by 13 by 13 cells. And this depends on the YOLO version that we have and we are using. Now, after that, we have the bounding box predictions. Here, basically, for each grid cell that we have divided, YOLO will predict multiple bounding boxes. And these bounding boxes are defined by the parameters. We have the x, the y, the width, and the height. Now, the x and the y, basically, guys, they are the coordinates of the center of the bounding box that is relative to the grid cell, while we also have the width and the height, and these are the width and the height, the actual bounding box that we have labeled. Now, after that, we have the class predictions. And for each bounding box that we have labeled in the step before, YOLO will predict the probability of the distribution over all of the classes that we have. Now, each class probability, guys, is basically associated with the object that is present in the box. Now, after that, we have the confidence score. And what YOLO does is that it basically, guys, assigned what we call a confidence score, each bounding box, representing basically the algorithm's confidence that the box contains basically an object. So basically, how confident is this? Are we sure that this is a car, for example? And the confidence score takes into account both the probability of containing an object and the accuracy of the bounding box coordinates. Now, after that, we have the non-maximum suppression. And basically, after predictions, a post-processing step, which is called non-maximum suppression or NMS, is applied. Now, this step, what it does, guys, is that it eliminates any redundant and low confidence deductions, keeping only the most confident ones. Now, as last step for the output, the final output will be basically a set of bounding boxes, and each are associated with a class and confidence score, representing basically the detected objects in the image. Here, for example, we can see after an NMS, we can detect this is a truck, this is a car, and so on. So basically, guys, YOLO, as we mentioned, processes the entire image in a single forward pass, making it faster than traditional step detection methods. Now, one more thing to mention, guys, is that the architecture is fully convolutional, which allows it to accept images of different sizes. And YOLO usually, guys, considers the entire context of the image during this detection process, which leads to even more accurate localization than other state-of-the-art models. Now, one thing to also talk about is that in YOLO, guys, each cell in the grid is responsible for predicting objects. Basically, if the center of the object basically falls within that cell. However, one thing to mention is that objects come in various shapes and sizes, which makes it difficult for a single cell to predict objects accurately using only one shape or one size. And this is where anchor boxes basically come in. Now, anchor boxes, just to explain them briefly, they are predefined, okay, and they have some fixed size boxes that the model uses to detect objects. And one thing to mention also is that each cell in the grid predicts the presence of objects based on these anchor boxes. The idea here basically is that each cell anchor box shape basically corresponds to a particular type of objects that the model is likely to encounter. So in the slide that we have here in this example, we have two examples. We have anchor box 1 and anchor box, as you guys can see here, and these could represent two different shapes or sizes. So for instance, anchor box 1 might be more rectangular to basically detect people, for example. So as you can see here, while anchor box 2, for example, might be much more square to detect objects like cars, for example. Now, if we look at this graph, it basically shows us the relationship between the number of parameters in different object detection models and their performance on the MS-GOCO dataset. Now, the MS-GOCO dataset, guys, is a standard benchmark in the field of computer vision, and it is used to evaluate the performance of algorithms on object detection as well as segmentation tasks. Now, if we look at this graph, guys, we can see that on the y-axis, we have the COCO object detection average precision, or AP. And this is just a measure of how accurately the model identifies and locates objects in images. And usually, guys, a higher AP value or average precision value indicates better performance. Now, on the x-axis, we have the number of parameters of the model measured in millions, which indicates the M letter. Now, the number of parameters, guys, is just a rough indicator of the complexity of the model. And more parameters often mean that the model has greater capacity to learn. It also can mean that it requires more computational resources to run. So what we want to usually just take away from this graph is that there is often a trade-off between the numbers of parameters in a model and its performance. However, something to keep in mind is that some models are more efficient than others, and basically they can achieve higher accuracy with fewer parameters. For example, we can see that the YOLO V8 and YOLO V9 models outperform many other models with a similar number of parameters. Now, also, it's also worth noting that models that are trained from scratch may perform differently than those that are pre-trained. And usually, guys, pre-training on a large data set, like for example, ImageNet, can give a model a head start, as it has already learned a lot of features that can be useful for object detection. So now, guys, let's put our knowledge into action with a hands-on session. So basically, what we'll do is that we will walk through the process of training and testing the state-of-the-art YOLO V8 model on Google Colab, which is a powerful platform for collaborative and GPU-accelerated machine learning tasks. Now, by engaging in this hands-on session, guys, you'll gain some practical experience in training and testing of the YOLO V8 model. So just a small explanation a bit about YOLO, about Google Colab, which we'll be using. So Google Colab is short for Laboratory, and it is a free cloud-based platform that is provided by Google, guys, and it allows us to basically write and execute Python code collaboratively. It also provides us with an environment that is similar to Jupyter notebooks, and it's particularly well suited for machine learning and data analysis tasks. So let's go on and start. Before we do that, guys, I'm gonna stop sharing my screen for a bit, so just I can prepare everything, and then we will be starting off. Now, if anyone, guys, has any questions, please feel free to ask me at any point, and I'll be more than happy to answer any questions you might have. So give it a moment. Okay, let's share the screen again. Hello, Ahmad. Unfortunately, not. You can use it, however, in OCR if you want to detect something. So, for example, let's say you are working on license plate recognition, okay, and you want to do something related to license plate. You want to read them. What you would usually do is, for example, you would have a YOLO model that detects these license plates, and you would add, let's say, another model below it to basically do the reading. So what would happen is that the model at first, the YOLO model would detect where the license plate is, and then you would have an OCR model that is able to read basically the text to tell you what these letters are. Does that make sense? So basically, you would be doing a multi-model approach. Uh, is that clear, Ahmad? Is it clear? Yes. So just to explain, YOLO can be used for segmentation, detection, and classification. It can be used for any of them, but it really depends on the version. So YOLO V8 is used for all of them. YOLO V9, I think currently it's only for detection. I'm not sure if they added something else, but currently YOLO V9 is only for detection. YOLO V8 can cover everything. And they can even cover pose tracking and many other applications as well. Is that clear, Ahmed? Awesome. Great, great. If you have any more questions later on, please do feel free to ask, or if you want, even feel free to connect with me on LinkedIn, and I'll be more than happy to answer any questions you might have. So now, guys, let's go on and start. So first of all, we're gonna start off by connecting our Google Lab environment, and we're gonna start off with the code. So first of all, we're gonna start off by importing all the necessary libraries that we need. First of all, we have the zip file library, which is just used for working with zip files. Basically, it allows us to extract and compress any files or folders. We are also importing the requests library, which is used to send HTTP requests. Okay. In this context, we will use it to download the dataset from the internet. We have also we are importing also CV2, and this is OpenCV. And OpenCV, guys, is a popular computer vision library which is used for image processing tasks, such as, for example, reading, writing, and even manipulating images. We also have Matplotlib, and basically Matplotlib is just a plotting library, and it helps us to basically plot graphs or even images. We have also the globe Python library, and basically it's just used for us to find the path names, which match basically a specified pattern according to the rules used by the Unix shell. And at last, we have two more libraries, which are random and OS. So random, it's provide basically functions to generate random numbers, as its name mentions. While OS is basically a Python library that provides a way of interacting with the operating system. Let's check the question. On a noise spill detection project from a dataset of segment the images into four classes, ships, Yes, sure, definitely, Muhammad. It would definitely be helpful to try it out, and I would definitely even check out the project that we do here, as it can be helpful. You can look into the Ultralytics library, and you can directly use the YOLO model for either detection or segmentation, whatever you are comfortable with, and it can definitely help with that. Yes, so it's Ultralytics. It's this one. Can you see it? So now in this tutorial, we will be seeing how to use it. So you'll get hands-on approach on what to do and how to use it and so on. All right, is that clear? Awesome.
Yes, see it.
All right, let's continue. So now what we are doing, guys, basically, first of all, we have just imported the necessary libraries for the task that we will be needing in the notebook. Now, after that, what we will be doing is that we will be using to install the Ultralytics library. So let's go on and run this. And the Ultralytics library, guys, is just a library that helps us out. Basically, it provides tools and utilities for various computer vision tasks, and it's particularly well known for its association with the YOLO object detection models. So currently, I think they have all YOLO models starting from YOLO v5 to YOLO v9. We can directly use, train, anything on this library, and it's very, very nice to use. So here, basically, guys, we are just installing the Ultralytics package, and basically because we will be using it. Let's give it a moment. So one more thing, guys, while it's downloading, is that we will be basically we'll be working with a substantial pothole dataset, which consists of over 7,000 images. Now, these images come from various sources, including the RoboFlow pothole dataset. There's also a research paper publication. There's also some manually annotated YouTube video frames and images from the RDD 2022 dataset. So basically, there's some careful annotation corrections. The finalized dataset compromises of 6,962 training images and 271 validation images. Okay, so this is the dataset that we'll be using. And what we'll be trying to tackle is pothole detection. So we'll be tackling that mainly. Now, this diverse collection, guys, provides us with a robust foundation for training and validating our models on pothole detection tasks. Yes, it is trained and basically it is a labeled dataset. Yes. Awesome, Ahmad. Great question. So now what we will be doing is that we will be downloading this dataset. So let's go on and do this together. So first of all, we'll be basically using the os.make directories line to basically create a directory which is called datasets. Okay, so let's check it out here. After running this code, we got the directory that is named dataset. Now, after that, what we will be doing basically is calling the cd command from Linux to basically just uh, change our current working directory to the datasets directory. So that right now we are working inside of this folder, and this is where the subsequent operations will take place. Now, after that, we have defined the download file function. And this function takes, as you guys can see, a URL, first of all, as an input and a file name as parameters. So basically what it does inside of it is that it checks if the file with the specified name already exists. If not, it uses the request.get function to download the file from the given URL, and it will save it with the specified name. So here, as you guys can see, we are calling the download file function. We are giving it the dataset zip file, which is uploaded to a Dropbox. And also we are saving it as a pothole underscore dataset underscore v8.zip. So now, once it's done, we can directly see that it has been downloaded to the current directory that we have decided on. So now it is as a zip file. And to do that next, what we want to do is to unzip this function. So what we have created is we have created an unzip function. Now, this function, what it does is that it takes a zip file as a parameter, and it will attempt to extract its content using the zip file class. So if successfully, basically, it will extract all the contents to the current working directory, so to the datasets folder. And if there's any issues, it will print an error message, which is invalid file. Now, after that, we are just calling this function. So if we check out here now, after the successful run of the function, we can see that the directory has been unzipped successfully. Now, if we look at the data, we can see we have multiple folders or directories. We have the training directory, we have the training to validation, and we have the validation directories. Each of them are formed in a way where we have one folder containing the images, and we have one folder containing the labels. Now, currently, they will not open because Colab will take some time to open them. As you guys can see, this is one example, as well as the labels as well, which are in the txt file format. So now that we have downloaded everything back to correctly, we will be using the cd command again to basically change the current working directory back to the previous one. So we will be going back one step to go back to the main current directory. Now, basically, guys, in summary, this section of the code that we just did basically sets up a datasets directory. We'll also download a pothole dataset that we have prepared from Dropbox. We'll also extract the content, and then it will return to the original directory. Now, this is a common workflow for preparing and organizing datasets in machine learning and computer vision project. Now, once we have done that, we have the data up and running. The next step would be to just go on and check it out. So we want to see this data, we want to see if everything is going well. And for that, we have created the following function. Let's go on and explore them one by one, and then we can see what they do. So first of all, we have the YOLO to BB box function. Now, this function takes the bounding boxes in YOLO format as input, where, as you can see, BB boxes is just a list that contains the center coordinates, which are x and y, and the dimensions, which are the width and height, which we mentioned that YOLO takes as input. Now, after that, what it does is that it converts these YOLO format bounding boxes into the format that is xmin, ymin, xmax, and ymax, which basically represents, if you want, the left and the bottom right coordinates of the bounding box, the top left and the bottom right coordinate. Now, after creating this function, we have another function which is called plot box. So what we do in the plot box function is that first of all, this function takes an image, you guys can see, and their corresponding bounding boxes, as well as the labels as input. Also, inside of it, it uses the YOLO to BB box function that we just defined to convert the YOLO format bounding boxes to the Xmin, Ymin, Xmax, Ymax format. Basically, we're just fixing the format of our data. Now, the function then normalize the coordinates based on the image's width and height. And for each bounding box after that, it basically draws rectangle on the image using OpenCV's cv2.rectangle function. And basically here, the rectangle is drawn with a red color, as we are specifying here, by saying that we want 0, 0 to 55. These are the RGB or the GBR values. So here we have 255 on red, and basically we are saying that we want this bounding box to be red. We are also specifying the thickness that is proportional to the image's width. Now, this code, guys, is just useful for us to visualize the bounding boxes on the images, which is often necessary when working with or basically on object detection tasks. Now, the last part or the last function that we have here is the plot function. Okay, as you can see, it is a bit complicated, so I'm going to explain it bit by bit. Okay, so I'm going to take some parts of it and explain them alone. Let's take this part, for example. Let's start off with this part. So first of all, what we are doing here is that we are defining a function that is named plot that takes 3 parameters. First of all, we have the image path, the label path, and the number of samples. So the image path is basically the path where the images are stored. The label path is basically the path where the corresponding labels with the bounding boxes information are stored. And at last, we have the number samples, which is the number where basically it's the number of the sample or if you want the images that we want to be plotted. Now, after this part, what we are doing is that we are doing a file path retrieval operation. So here we are using the all images. Basically, we're using the globe module to find all the files with the extension JPG or .jpg in either small or big letters in the specified image path directory. Now, after that, the file paths are then basically stored. Now, after that, we are doing a random image selection. Basically, here we are determining the total number of images in the data set. And here we have also a loop. So as you can see, we have here a loop to basically iterate over the specified number of sample images, so the number of samples. And for each iteration that we have here, random index, which is going to be called J in this case, select choose a random image from the dataset. Now, after doing that, we have an image processing step. And here what we are doing is that, first of all, we are extracting an image name from the file path, but basically splitting it based on the file separator and removing the file extension. Now, after that, the actual image will be loaded randomly using OpenCV's cv2.imageRead. So this image will be a random image that is loaded using OpenCV. Now, after doing this part, let's go on to the next part, which is the following. So from here, let's go to here. Okay? What we are doing here is that, first of all, we are reading the label information. We are opening the corresponding label file, so the TXT file for the current image, and we are reading its content. Now, the content of the label file contains information about the bounding box and labels. And for each line, basically, guys, in the label file, it will extract the labels and the bounding box information. Now, after that, we have the bounding box and label processing. Basically, here, what will happen is that we will be taking the bounding box information and we will be parsing them and converting them to a list of lists, which we are mentioned here by BB boxes. Okay. And also, guys, the labels are also extracted and are also stored in a list too. And the bounding box information is in the YOLO format. So we can see here, we have them as center coordinates, x, y, width, and height. Now, for the final step would be the plotting. What we want to do is just plot the images that we print. And for that, we would be calling the plot box function that we defined previously, draw bounding boxes on these images. And the resulting image is then basically plotted using matplotlib. And basically here, guys, the loop will continue for the specified number of samples that we have defined. And the final display basically includes a grid of images with their respective bounding boxes. So in summary, guys, this is a bit of a complicated function. But what we are doing here is that we are processing and visualizing the images with their bounding boxes and labels from the specified data set that we have. So it's just a useful tool for us to inspect the annotated data and ensure the correctness of the bounding box annotations. So now that we have done that, guys, we would now call plot function with these specific parameters. First of all, we are giving it the image path, which is the training image path. We have also the label path, which is the training labels path. And we have the number of samples, which we are here setting to 4, indicating that only 4 random training images will be visualized. Now, if you go on and call this function, we're going to see the following. So here, basically, guys, the plot function will process the entire images and their labels from the specified paths, and it will randomly select 4 images, and it will display them for us along with their bounding boxes and labels for us to just see the data quality and how the data looks like. If we take a look here, we can see that the data, how the data is labeled. We can see that this is a pothole that is labeled by the data. We can see that these are some potholes here as well, and here too. So if we go ahead and run this one more time to take 4 more random images, for example. Let's give it a moment. Okay, so we can see this is another execution. We can see that this is a pothole that was labeled. This is a pothole that was labeled. This is a full pothole that was labeled, and this one too. We can see how the data that we have looks like and how the labeling is done and so on. So now that we have basically explored, basically, guys, our data, we can go to the next step. Now, before we do that, guys, I just want to make sure that everyone understands what we're doing. So the code that we did is just a practical way for us to visually inspect a subset of the training images and ensuring that the data is correctly annotated and providing an understanding of how the model will perceive and learn from these images during the actual training. So now we go to the next step. So the next step here, guys, we are using the Jupyter Notebook command, which is called write file, write content into a YAML file, which is called, pothole d8 YAML. So let's break it down a bit. So for Ultralytics to work, it would usually require us to give it a YAML file as input. And this YAML file, we want to contain all the passes for the data, for the training data, for the validation data. So it has an expected input or a way of input for the data in general. First of all, we have the path, basically. This basically, we are specifying the root directory path where the data set is stored. Now, in this case, it's set to the pothole dataset v8 directory, which is basically here, if you take a look, it's this directory, guys. Now, after that, we are indicating that the path of the training images within the dataset is set to the train-images. So basically, we are setting it to this directory, suggesting that the training images are located in the train directory under the root dataset path. Now, after that, we have the validation path in which we are setting it to the valid-images path. And here, basically, we are indicating that the validation images are located in this directory under the root dataset path. Now, after that, we have the class names. So here we are defining the class names that are used in the dataset. So first of all, we have names, and we have here we are assigning the, if you want, the class label 0 to the class name pothole. Now this indicates basically that in the dataset, the class pothole is represented by the numerical label 0. Now to answer your question, Muhammad. So in your case, Muhammad, if you're working with four classes, you would have here four class names. For example, zero for ship, one for sea, two for land, and three for oil, for example. And you would label your data such as this. And basically, you would be able to directly train a segmentation or a detection classification model. So I hope this is clear. So now let's go on and create this YAML file. If we go on and refresh now, we can see that it has been created here. We can open it and check it out, and you can see that it was created. So now, guys, one thing to mention is that this YAML file that we created basically serves as a configuration file for the dataset, and it provides us with information about the directory structure and class label. Now, it is commonly used in machine learning projects to basically be able to streamline the process of loading and managing datasets. Now, before we go into starting off with the training, one thing that I would like to mention is that we have usually multiple, if you want, YOLO V8 models. We have basically different models with varying complexities and sizes to cater to different deployment scenarios. I'm going to talk about them briefly. First of all, we have the YOLO V8 Nano model or YOLO V8N. It is designed to be the most lightweight and efficient version of YOLO V8. So it is optimized for scenarios where computational resources are very limited, which makes it suitable for deployment on edge devices with lower processing. We also have the YOLO V8S, or the small model, and this model strikes a balance between model size and performance, offers a bit more complexity than the nano model, which makes it suitable for applications where a modest increase in computational requirements is acceptable, but efficiency remains a priority. We also have the YOLO V8 medium model, and basically this also provides a further increase in model complexity compared to the small model, and it aims to strike a better balance, if you want, between accuracy and computational efficiency, which makes it a suitable choice for applications with, if you want, a moderate amount of computational resources. And we also have the YOLO V8 large and X large models, which are also for larger computational resources. Now, in our training that we'll be doing now, we'll be focusing on using the nano model, which is the YOLO V8N. And this choice is driven by the lightweight nature of the nano model, which makes it ideal for scenarios where computational resources are constraints, such as deployment on edge devices or mobiles or even systems with limited processing powers. Now, training on the nano models will allow us to achieve real-time object detection with minimal on-system resources. So now let's go on and start with a YOLO V8 nano training, and you'll see how simple it is, guys. But let's break down the code. Basically, this is the code that we can directly start off with the training. So first of all, we are starting off by setting the number of training epochs to 5. And epoch, for those of you who don't know, guys, an epoch is one complete pass through the entire training dataset. Now, after that, we can directly call the ultralytics command. And what we are doing here is that we are initiating the training process using the YOLO command line tool that is provided by the ultralytics library. So first of all, we're starting off by defining the task, which is detect. So here we are specifying the task that we want to do, which is detection. After that, we are specifying the mode, which is going to be training. So basically, here we are indicating that the model will be trained. After that, we are specifying the model. And here we are specifying that the YOLO V8 nano model to be used for training. So as we said, we're going to be using the nano model. We have after that the image size. Here, basically, we are setting the input image size to 1280 by 1280 pixels during the training. Now, this is something that can be changed depending on your needs. Now, after that, we have the data key. And here we are specifying the YAML configuration file for the dataset. After that, we have the epochs, which we have created already and defined as 5. We have also the batch size, which we have set to 8. The batch size basically is the number of samples that are processed before the model's parameters are updated. And at last, we have the names parameter, which basically specifies a name for the trained model, indicating it's the YOLO V8, basically nano model trained for 5 epochs. Now, this code basically, guys, will initiate the training process for the YOLO V8 nano model, utilizing basically the specified configurations and hyperparameters, as well as the data. So this is just a sample of how to use it, guys. You might adjust them in practice based on the specifics of your data set, hardware constraints, and even your training goal. Perhaps one more thing to mention is that we will not be going through with the training. It will take a while. So the training process will take us around maybe 10 to 20 minutes. So I won't be making you wait for that. So I already have trained the model previously and saved it previously. So we'll be going on from there. So at the moment, I have just stopped. And what I'll be doing next is loading the model that I have trained and saved previously. So we'll be doing that basically in the steps. So I'll be explaining how I'm doing it. So first of all, what we are doing is that we are basically mounting our notebook basically to my Google Drive, Google Colab, and I'm gonna attempt to copy the file from my Google Drive. So basically, when I train the model, I saved it in my Google Drive account, and this way I can directly mount it to my notebook and directly copy anything from it. Yes, yes. I'm more than happy to send it. So if you want, feel free to reach out to me, and I'm more than happy to send it. All right. Awesome. My pleasure. So just to continue what we will be doing, we are here just mounting it. We were mounting the model from Google Colab to our Google Drive in the Colab environment. So basically, after that, it just prompts the user to access their Google Drive. Now, after that, what we will be doing is that we will be copying the files. We will be using the cp command, which is Unix based, to basically copy the files or the directory. Basically, we are copying the weights, so the model that I have trained before and stored it in my drive to this directory where the trained model would have been saved. If we go on to this directory together, which is runs, detect, YOLO V8, and we can see inside of the weights now that we have the best.pt model, which is the model that I have trained previously. So basically, guys, in summary, what I've done here is that I have mounted the Google Drive to the Google Colab environment, and then we're copying the file named mess.pt from a specified path in Google Drive to a specific directory within the Colab environment. Now, after that, let's say we have trained the model, it has been successfully trained. The next part would be to go on and evaluate it. So we want to see if this model is good. So what we want to do, what we're gonna do it basically this way. Let's go on and explore it. First of all, we're gonna be definitely using the YOLO command like we did before, and this command basically to call the Ultralytics library. After that, we're gonna define the task as well, nothing new. But here the only difference is that we are defining the mode as val. So here we are specifying that the evaluation will be performed on the validation set instead of train like we did before. So if you check above, was train mode. Now we are doing val mode to validate. Now after that, we have the model. Here we are specifying the model weights, where they are, where the model is that we trained, which is in this directory like we have here. We are also giving it the name, as well as the data, which we are specifying where the YAML configuration file is for this data set. So let's go on and run this together. And here, guys, this command basically will evaluate the YOLO V8 nano model on the validation set using the specified weight file. Now, the results of this evaluation, such as precision, recall, and other metrics will be printed to the console, as well as they will be saved and we'll be seeing them together. So let's just give it a moment to finalize it. Now, if we refresh here, we're going to see that the YOLO V8 evaluation folder has been created. And there you go, guys. We have finished the evaluation. if we check the metrics, we can see that we have run the evaluation on 271 images. Basically, we can see that the precision is 0.6, the recall is 0.4, the MAP is 0.4, as well as the rest. So these are not perfect metrics. We can train the model on more, say, epochs, a higher batch size, and so on to make it better and maybe improve it later on. Now, the next part is to basically look into a bit the metrics that we're going to be. So I'm going to explain them briefly. So here in this image that we have here, this is called a confusion matrix. And a confusion matrix, guys, is just a table that is used in machine learning to evaluate the performance of a classification algorithm. So it basically provides a detailed breakdown of the model's prediction compared to the actual ground truth across different classes. So as you guys can see, the confusion matrix consists of four main components. We have the true positives, we have the false positives, we have the false negatives, and the true negatives. Yes, Muhammad, it will be definitely shared. We will see how to share it, okay? But it will definitely be shared. Now, basically after that, let me explain them briefly. So the true positives, basically, they are the instances where the model correctly predicts the positive class. So for example, in a medical diagnosis context, true positives represent the cases where the model correctly identifies patients with a specific conditions. Now, for the false positives, basically it is the instances where the model incorrectly predicts the positive class when it should have predicted the negative class. For example, let's say in a spam email detection scenario, false positive occurs when non-spam email is mistakenly classified as spam, for example. Now, for the false negative, and this is where the instances where the model incorrectly predicts the negative class when it should have predicted the positive class. So it's directly the opposite. For example, in a fraud detection application, false negative happens when the model fails to identify a fraudulent transaction, for example. And we have, at last, we have the true negative. And this is the instances where the model correctly predicts the negative class. For example, in a binary sentiment analysis task, true negative represents cases where the model correctly identifies non-negative sentiment. Okay, as you can see, this is how the confusion matrix is often arranged. And one last thing to mention is that we can get multiple other metrics from the confusion matrix, which are the following. So I'm just gonna explain them briefly because we've seen them. First of all, we have the precision. And the precision, we have seen it here together. So this is what it is. This is the P. It stands for precision. Now, precision, what it does is that it measures the accuracy of positive predictions and is calculated as true positives divided by true positives plus false positives. Basically, it answers the question of the instances that were predicted as positive, how many are truly positive? We also have the recall. The recall basically is this one, it's the R. The recall, guys, is basically its sensitivity or the true positive rate, if you want. We can call it that. And basically, recall, it measures the ability of the model to capture all the positive instances, and it is calculated as true positive over true positive plus false negative. So basically, what it does is that it answers the question of all the true positive instances, how many did the model actually capture? And at last, we have the accuracy, which we can also see here, basically the MAP. And basically, the accuracy, guys, is overall correctness of the model. It is calculated as true positive plus true negative over true positive plus true negative plus false positive plus false negative. Don't worry about the formulas. You can find them online, but I have them studied. And it answers the question of how many predictions were correct out of all the predictions. Now, understanding these components, guys, in the context of a confusion matrix is very crucial to be able to evaluate the performance of a machine learning model, especially in binary classification tasks. So now, also, guys, one more thing to mention is that now what we will be looking at, once the evaluation task runs, it will give us a confusion matrix of our model, so how it's performing. So if we run this code here, we are able to take a look at our confusion matrix and how it's performed. So if we take a look here, for example, we can see that the model that we have has correctly predicted potholes around 400 times. So this is 392. It has basically predicted a pothole when it wasn't. Sorry, let me check again. Sorry, my bad. It has correctly predicted a pothole when it was. So this is the positive 324 times. If you compare this, it has 325 or 225 false positives, 292 false negatives, and zero true negatives. This is something I wanted to mention for you. Now, also, guys, we can check some other metrics from the images we get as outputs. We can get some curves of the confidence curve, the precision recall curve, the precision confidence curve as well as the recall confidence curve. And you can see how the model is improving epoch by epoch and how the accuracy is increasing as well as the confidence and so on. And these can be used for analysis purposes and how we can use them. Now, one last thing that I think I should mention is the F1 score. I've already explained the precision and the recall. The F1 score, guys, is a metric that basically combines both the precision and the recall into a single value. So it is practically useful in situations where there is an uneven class distribution. So where, for example, you don't have a balanced data set, and it has a formula of, I think, F1 is equal to 2 times precision times recall over precision plus recall. And we have seen them previously. So these are some evaluation metrics that we get for our model from the Ultralytics library when we run the evaluation command, and they will help us to evaluate our model successfully. Now, after doing that, what we want to do, now we have seen the model, we have evaluated, and we think it is good. We want to start off by doing some inferences, and we want to just visualize it. We want to visualize the results. We want the model to do if you want, the predictions and save them somewhere where we can see them. So to do that, what we will be doing is basically use the same command, but we would have to change the mode to predict, okay, as well as the name to YOLO V8 Nano and infer, okay? And we can mention that we want to hide the labels and just run it. Okay? So let's go ahead and run it. And it would, I think, a minute or two to run. Let's just do that. As you can see, it is running model prediction on each image of the validation dataset one by one. And we can see also that it is taking around 29 milliseconds only to predict on an image, which is a very, very quick time. So let's see. So let's refresh here. We can see that we will get a new folder after this. We can see that the YOLO V8 infer is here, and it will contain all the images with the bounding box. Okay. So now to see them, we have the visualize validation results function. And this visualize function will allow us to basically just visualize the results and plot them and visualize them in a 2x2 grid. So let's explain the code briefly. As we mentioned, first of all, it will take as input two parameters. First of all, we have the result directory, which is the directory containing the images to be visualized. And also we have the number of samples, just like before, which is the number of images to be plotted in the grid. And we have set it here to 4. After that, to plot a 2x2 grid, we are using the matplotlib function to basically create a figure with a size of 20 by 12 inches. And we are using the globe function to obtain a list of the image file path within the specified result directory. And the paths are then just shuffled randomly to get 4 random images and display them. After that, we are just looping over the images. So we're just iterating through shuffled list of image names. And for each image, we are reading the images using the plt.im read function. And after that, we are just plotting these images basically in a subplot of a 2x2 grid using the plt.subplot function, as we can see here. And after that, we are just breaking out of the loop and we are displaying these using the type layout and the plt.show function. So, guys, this function is just designed to provide a convenient way for us to visually inspect a subset of images. And in the context of object detection, these images will likely, as we mentioned, will include the original image along with the predicted bounding box and labels overlaid on them. So let's go on. Now we are calling the visualize function with the path where the visualization are stored. Let's go ahead and run this. So it will take a few minutes. So guys, if you have any questions during this, please feel free to ask me. And there you go, guys. This is one example. We can see that the detections of the potholes. If you want, we can try one more example of the images. Let's see if we have closer images so we can see them. Let's give it a few seconds. And as you guys can see, this is one prediction for a pothole, for example. Let's try one more run, hoping for closer images. So anyone, guys, if you have any questions while we're waiting, please feel free to do so. And basically, guys, you can see here the model has detected the correct, basically, potholes and so on. So basically, guys, this is a small example of how to use the YOLO object detection model. Basically, this is it. I hope you guys enjoyed it. And please, guys, if you do have any questions, please feel free to reach out for further discussions or questions. Feel free to connect with me on LinkedIn by scanning the QR code that is provided. And again, guys, thank you for joining this exploration to YOLO object detection. And again, if you have any inquiries or need any additional clarifications, I'm here to help and very happy to help. And again, pleasure meeting everyone. So one last thing to mention is regarding the notebook. If you guys want me to share it with you, please feel free to reach out to me on LinkedIn, and I will share it with you directly. Okay, guys? Can you hear me, everyone?
Yes.
Awesome. All right. So again,
Thank
guys,
you.
if you do have a questions, now is the time. And if you need the notebooks again, please feel free to reach out, and I will share it with you on LinkedIn. My pleasure, Ahmad. My pleasure. My pleasure, Muhammad. I hope you guys enjoyed it, and it's a pleasure meeting you guys.
Thank you, Jen. It was very interesting.
Thank you. Thank you. My pleasure, guys. Have a great day, and hope you guys enjoyed the content.
Bye bye, Jen.
Bye.
And
Bye, guys. Bye, everyone.
thank you everyone for attending the tutorial. We will have a break now and see you back here at 5:30. Bye bye.
Bye. Bye. Bye, guys.